So far we've looked at the two major things with our properties, and that is that I know my normal force is the load over the area, and I know my strain is the deformation over the length. So these properties have a relationship, especially when we graph the stress versus the strain. So let's talk about it, but first let's talk about how do we measure this. And so what we have here is this is a Super L machine. This is similar to what we have in the lab. This picture's from, I think this picture's actually from the 50s, but it doesn't really matter because technologically wise, it hasn't really changed all that much. So what we have here is we have a device where the important thing is they sample the dog bone. If we look over here, this guy right here, that should look familiar to you because you made it as a freshman. And so this is really nice because I think there's a lot of closure in being able to destroy something that you've created. So we're going to take these little dog bones that you made as freshmen, we're going to stick them in the machine, and then we're going to test them till failure. So what happens is that this crosshead, which are these two guys right here, they will end up applying load. And the way that it does that is this bottom crosshead will move down, and it will stretch the material, and it will keep applying load until it breaks. Now, the crosshead itself is measuring the amount of force, and the way that we measure the amount of strain, because remember, strain is going to be the deformation over the length. So you know the initial length because you've set that up, and you've got this little device here that's called an extensiometer. And the extensiometer measures strain. And typically they're used with very high-tech tongue-tied this morning, piezoelectric device that measures very small amounts of deflection. So as we pull on this thing, we're measuring the strain, and then we can plot the stress versus the strain. Now, the stress is all going to be based on this initial diameter of the material, and even though the diameter will change as we're pulling on it, we keep it on that initial diameter. So let's take a look at our stress strain graph. Now this is a example of SKS. SKS stands for some kind of steel. Doesn't really matter what kind. This is a full-blown graph of a steel that actually will show all four zones of the material, all of the behavior, which we don't always have in a material, but we can have it, so we have this one here. And so this blue line that we see here, this is the stress strain curve. Now, remember, I said that the diameter is going to change as you pull on it because it's going to get slightly smaller. That's what this line here represents, because all of this is based on the initial diameter as the force is going through, and the diameter changes, the force is going to be changing. It's always going to be going up. This doesn't represent that because it is on that initial diameter. This line shows you what it would be if we actually took into account that the diameter is going to change, but we're not really going to worry about that right now. First thing that we need to do is we need to talk about the difference between elastic and plastic behavior. There are two types of deformations, elastic and plastic deformation. So you can see the elastic deformation is here. It's a very short part of our graph. Elastic behavior means that when the load is removed, all the strain will go away. It'll snap back like a rubber band. We'll have no more, you won't even know it's there. The much larger range here is what's called plastic behavior. Now, plastic behavior is when we've put so much force into a material that we're permanently changing the material. We are stretching and reordering the atoms and the crystalline structure of the material, so it's changing. We're going to be talking a lot about these two in the next couple of lectures. The important thing with the plastic behavior is when you let go of the material, the strain doesn't go away. A little bit of it will. The little bit that we've had from this elastic behavior will go away. But we are going to have some permanent deformation. And as I said, we're going to talk about that in the next couple of lectures. So let us talk about what's going on. First of all, let's talk about the four regions, and then we're going to come back here and we're going to talk about these points that are labeled on here. So the first region that we have here is the elastic region. So the elastic region is where our material is exhibiting elastic behavior, which means if we remove the load, it goes away. Pretty simple. So the plastic regions are all these regions that will include some kind of permanent set of the deformation of the material. So we have three main regions. Not all materials will show this, but once again, this is our generic steel that's going to show all four. When you do these things in the lab, that first region, the yielding region, you won't see in aluminum. So let's talk about it. So the first region is the yield region. This is also called the perfectly plastic region. So what's happening here is the material is continuing to elongate with no increase in stress. And so that flattens out, everything goes away until we get into the strain hardening region. So the strain hardening region is we start to get a decrease in the diameter of the bar, and it's increasing all evenly. So everywhere up and down the bar, the diameter is just all uniformly decreasing. You've probably heard of strain hardening before, especially if you listen to truck commercials on TV, because they'll talk about we use strain hardened steel or strain hardened aluminum. So basically what we're doing in the strain hardening is we're making the material harder. It is able to withstand more stress. Of course, the thing is it also gets a little bit more brittle. We'll talk about what that means here in a second. And eventually we strain harden things so much that we can no longer strain harden it anymore, and it begins to fail. And it goes into the necking region. And so what the necking region is that region of the graph where the bar has locally started to reduce in diameter at one location. And this is, once you get in the necking region, you're in the point of no return. The bar is going to break. And it's going to get that region where it's locally starting to shrink is going to get smaller and smaller and smaller until it finally breaks. The interesting thing, and one thing that I always like about the necking region when we think about bars is, so back in the 50s, someone at MIT wrote their PhD dissertation on this phenomenon. And what's really interesting about this is necking used to be the slang for, at least for my generation, it was making out. I have no idea what the slang is for your generation. And truthfully, I don't really care because I just don't need to get into that. But so this was the slang for making out and whatever. But anyway, so his PhD thesis was titled Necking in Bars. And that had a completely different connotation when you were outside of engineering. But I just think it's hilarious that at that time there's a PhD dissertation right now at MIT called Necking in Bars with what everything meant at that point. Anyway, so back to engineering. So we have these points labeled on here. Especially, we've got this cluster of points right here. It's kind of interesting. The proportional limit, the elastic limit, the yield stress. So what are those? Well, if you notice, if we look here in the elastic region, also we call it the linear elastic region, it is a linear line until it hits a proportional limit and starts to tail off at the top. So all the proportional limit is it tells you where the stress versus strain curve stops being linear. It's still elastic after that, but it's just where it stops being linear. The elastic limit is where the material will go from elastic to plastic behavior. Now, this one's interesting because not all materials do this, but like with a lot of steels, what you'll see is you'll see a little hump, and it'll flatten out into the yielding. The elastic limit is right there. It's defined as that top of the hump. Now, if you got something like an aluminum, which doesn't have the yielding region, it immediately goes into the strain hardening. So the question with this guy is, okay, well, where does the elastic limit end? Because we can't really tell. We can't use the end of the linear elastic region. Can't use the end of the linear region because if we look at that right there, well, the proportional limit's well before we stop elastic behavior. So what do? What we do is we use a defined yield stress for everything. And so what we do is we go, okay, I'm going to look at where my strain is 0.2%. Then I'm going to draw a line that's parallel to my linear elastic region. And then wherever that line that's parallel to my linear elastic region that starts at 0.2% strain, I am going to define that as my yield stress. So when you go and look up yield stress in a materials property table, you will not be getting the elastic limit, you will be getting the defined yield stress. It's a constant thing, so we're defining all materials the exact same way. Is the yield stress the same as the elastic limit? Are they going to be at the same stress value? No. But we always design against the yield stress. That's what we're looking up. And once again, the reason we do that, not all materials will do this. So we need a consistent way of defining the yield stress. So if I go to aluminum here and draw it in, I go, oh, that little point right there, that's my yield stress. How do I know it's my yield stress? Because that's what I've defined it as. So those are all very important points. The last 2 points are the ultimate stress up here. The ultimate stress is kind of that point of no return. We've put all the stress in the material we can. After you hit the ultimate stress, it's going to begin to neck. And the last one here is the fracture stress. Your textbook will call it the breaking stress. I don't like that connotation because then they'll talk about sigma sub b, sigma breaking, which is also the exact same thing as the bearing stress. But fracture stress, breaking stress, both mean the same thing. It's all fine. This is just the stress value at which the fracture occurs. There's a lot of information in this graph. There's actually a lot more than what we talk about in this class because we really don't get into strain energy too much in this class. Typically, maybe towards the end we'll talk about it. It's all about this area under the curve and what's going on. Pretty cool stuff. Unfortunately, we don't cover it.